We will be looking into the impact of interior thermal comfort on student health, productivity, and performance through conducting a literature review, investigating criteria to achieve thermal comfort at schools, including 3 examples that have incorporated thermal comfort, and conducting a comparative analysis of 2 schools as case studies. Let us start with the introduction. Children spend around 1/3 of their day at schools, where they are expected to engage all their senses as they embark on their learning journey. From there comes the need to ensure school indoor and outdoor environment is ideal for students' learning and development. Any indoor space is subject to indoor environment quality, which can be categorized into thermal comfort, indoor air quality, and acoustic and visual comfort. Several studies proved that poor IEQ at schools leads to deterred learning and performance. It also leads to discomfort, distraction, and health issues such as headaches, confusion, nausea, and even eye allergies. On the other hand, improved IEQ is directly correlated with positive growth and education of school children, resulting in cheerful, energetic, and more creative students. According to Corsavi et al., thermal environment comes first, followed by indoor air quality, then acoustic comfort and visual comfort. And that is because it incorporates many aspects of the indoor environment, such as the ones shown. Thermal comfort is defined as the condition in which the mind expresses satisfaction with the thermal environment, so no need to shiver or sweat to reach the body's thermal equilibrium. At the same time, it is dynamic and is perceived differently depending on space design, economic environment, cultural background, and student age. It is crucial to ensure thermal comfort at schools because students are significantly affected by temperature extremes due to their poor self-regulation and higher metabolism. Moving on to literature review. Google Scholar, ScienceDirect, and reference lists of chosen articles were explored for papers since 2016. As for the impact of thermal comfort to health, a study in Finland related respiratory complaints of students to interior spaces being too hot or too cold. A study in Portugal determined that the thermal insulation from clothes can influence student well-being and learning process. Another study in Selangor revealed that hot classrooms caused headaches and students' stress. Now to thermal comfort and student performance. Jiang et al. Studied the impact of controlling the thermal comfort parameters to conclude that thermal comfort had positive impact on student learning, performance, and well-being. An extensive literature review has revealed that students need task-dependent conditions of IEQ to benefit most. A study to find the most comfortable temperature concluded that the best performance is 5 degrees less than that recommended by international standards. Another study revealed that male students performed better as temperature was closer to the higher limit of comfort compared to females who preferred lower temperatures. And finally, another study proved that the best performance was 1 degree less than that recommended for comfort. Moving on to thermal comfort and student productivity and achievement. A study found positive correlation between thermal comfort and student SAT test score. A research has concluded that thermal comfort that was enhanced by natural ventilation was directly related to better mathematical test results. An investigation concluded that memory in specific was enhanced in warm environment, while attention was enhanced in relatively cool environment conditions. It is clear that thermal comfort is directly related to students' well-being, performance, and productivity. Moving on to criteria and examples. Modern technology paved the way for better indoor environment through the use of active heating or cooling strategies. At the same time, history shows that people since ancient times have tried to achieve better interior thermal conditions through the use of passive heating or cooling strategies. Let's look into criteria 1. Several studies are looking into energy efficiency and occupant comfort to reach equilibrium where energy usage is optimized and thermal comfort is not jeopardized. An investigation of active heating and cooling revealed that closing hallway doors and reducing the temperature set point of HVAC allowed for expanded HVAC daily operation time, thus increasing thermal comfort. Moving on to criterion 2, ventilation. For Mediterranean regions and other hot climates, ventilation is an important cooling strategy that needs meticulous design depending on window placement, window-to-floor ratio, and direction of air movement. Exploring this criterion, a wind tower assisted by solar chimney resulted in 106 more hours of comfort during February and 170 more hours of comfort in August. Moving on to shading. Shading is used to control the amount of solar gain in natural light for glazing to result in better thermal and visual comfort. This criterion was explored in a study that concluded it is best to apply vertical shading to the school's west-facing windows to achieve a reduction of 2.5 to 4.5 degrees Celsius in indoor thermal conditions. Moving on to insulation. Just like clothes, insulation restricts heat flow, thus reducing heat loss in cold weather and heat gain in hot weather. It highly impacts energy saving and is applied to every part of the building to ensure resistance to heat flow. This criterion was investigated using computer simulation to look into whether it is better to place additional insulation inside or outside the thick brick walls of two schools. The study revealed it is best to place insulation on the exterior. Moving on to examples to understand the process of thermal enhancement better. The following study focused on finding whether the renovation strategies done on one of the oldest schools improved the thermal comfort or not. Analysis revealed occupant discomfort, where in the warm season several students felt slightly warm, and in the cold season most students felt cold and cool. Refurbishing the old school resulted in worse thermal conditions represented by the dark red line, especially during the warm season. For that reason, the researchers suggest locally suitable strategies that could enhance thermal well-being. This example proposed a passive wall system for a prototypical classroom. The proposed wall design is made of 20 cm porous ceramic that is filled with water for evaporative cooling. The ceramic is sandwiched between two layers of brick. The strategy was modeled using CFD software. Generally, the air temperature is extended between 26 and 54 degrees before activating the proposed wall system, and between 14 to 28 degrees after activating the system. The graph on the right compared to the left shows the air velocity with almost 50% decrease in temperature when passive wall system is deployed, thus achieving better conditions suited for thermal comfort. In this example, phase change material shading system shown here on the right was applied to enhance the annual energy performance and improve thermal conditions. The building was simulated to measure the impact of phase change material or PCM shading. PCMs used are presented in this table. Note that PCMs have the ability to absorb and release thermal energy to maintain regulated temperature. Adding PCM shading has increased comfort by 34%, mainly during the summertime, and reduced peak temperature by 2%.
Shading system alone resulted in 41% decrease in cooling energy compared to 44% with PCMs applied.
Moving on to the final stop. The following schools will be analyzed and compared. This is a table of information on both schools. The school in UAE will be referred to as Building A, and the other one is Building B. Building A is a typical courtyard school and Building B has a rectangular form. After an extensive research, the two case studies were paired for these reasons. Analysis found that the building consumes more energy than that recommended by the building rating system of Abu Dhabi, with 80% of the consumption attributed to air conditioning. The school was divided into 5 thermal zones using Design Builder. The authors evaluated 3 main strategies. Electricity for space cooling was reduced most when all strategies were combined, resulting in better interior thermal environment. The criterion of using natural ventilation for passive cooling was also proposed, and CFD analysis revealed the following results. Unlike Building A, the study on Building B began with an assessment on internal conditions through assigning thermal zones in Design Builder. The thermal conditions of School B were evaluated hourly using Fanger's PMV index depending on the environmental conditions, revealing discomfort mostly in the seminar rooms represented by the red square. Several strategies were simulated and then combined to result in improved PMV and 18% increase in comfort. The enhancements also resulted in 34% improvement in typing and 33% in thinking, but at the expense of 11.7% increase in annual energy. The major difference between the two buildings' procedure lies within the energy inclusion timeframe. In School A, the whole process of school refurbishment was proposed to enhance energy, while for School B, energy analysis was a byproduct of internal thermal enhancement strategies. The advantage of energy saving for School A did not come at the expense of well-being. Research has shown that buildings of high energy efficiency provide high parameters of thermal comfort. As for School B, further analysis can show that thermal enhancement should not necessarily mean increased energy. There's a growing body of research relating thermal comfort to student well-being. Papers mostly looked into thermal comfort enhancement impact on well-being or thermal parameters enhancement on energy saving. Research on educational buildings should be more inclusive of both topics, just like the example of the educational building in Istanbul, referred to as School B, to have a more holistic approach to both thermal and energy enhancement.